Hey everybody, welcome back to the channel. So we are sitting here at my desktop on Fusion 360. Today we are going to, on this video, is only going to cover machining this part here because it's the most complex to date for me. There's machining done on all 6 sides of the stock. So we'll get started right here on the setup portion of it. We start out with a face mill, this only skimming 0.010 of an inch just to true the top surface. And then we move on to an adaptive. Alright, so here's where the big deal started. I generally record my cam portion after I do the video, shoot all the machining portion of it, so that way I can kind of put on things that I've learned and make changes to the CAD, because I'm going to offer all this CAD as a package for making your own ATC. So anyways, in the beginning I had a 1/2 inch end mill, and I never used it before, and I've never used a 1/2 inch end mill as far as on this machine, so I don't have a recipe. So I tried to go with some of the basics, and it ended up being terribly wrong, and I was getting horrible tool bit chatter because the spindle RPM was too much for the feed rate. I could speed the feed rate to max the machine could go, and it quietened it down dramatically, but it was still apparent when it would go around corners, etc. But I ended up trying to make changes to it, and I come back and started the machine again, and I ended up breaking the end mill because I made the wrong change. So but I was able to salvage the part because it broke way out here with trying to get rid of the excess. So anyways, I switched to a 3/8 end mill, which I had known good recipe for, and it was working well, but it required me to do multiple step downs in order to do this. I still had to do step downs with the 1/2 inch, but not as many. So anyways, we start out with an adaptive, and that goes around and it just cleans up the excess material, because this is 5 inches and on the x-axis. So the adaptive has a step over our optimal load of 40 thousandths. We're leaving 20 thousandths for the on the radial, not the axial, and like I said, 3/8 end mill at 6,500 RPMs at 48 inches a minute, and it works great. I get good surface finish with that. So then we'll move on to, after this we do a contour of this, so we clean that up with our finishing pass. Again, multiple step downs, same tool bit, and then we do a pocketing sequence here. Now I should have trimmed it up a little bit. This is done with an open chain when I selected the area to machine, but for some reason I didn't trim that up, so I ended up machining air out here. So if you don't want to machine air, really check that. So it was a learning thing for me again. These are multiple step downs. The optimal load is still 40 thousandths. Radial stock to leave, same speed, spindle speed, and feed rate. So yay, that was all machined out great. And then we do an adaptive. We do an adaptive again, and that cleans out this bottom pocket. This is where the pulley on the stepper motor goes through, and then contour for that, and a contour for that. Then we do a bore cycle. Now, something I learned in the previous, I like to bore all the way through and get in case I need to zero the part again, so I'll have an origin or a reference point. The downfall with that is the hole was extremely deep, so I had problems with chip evacuation, so I have a lot of re-chip cuts. And the scoring, luckily it's not in the bearing pocket, it's only in the opening, so it's meaningless, but it's worth a note. Trying to get the chips out of there and you're recutting them, it ends up affecting the surface finish dramatically on the inside. So even if I wanted to use that as a reference, it would have been a terrible reference point because of the poor surface finish on the inside this point right here where it's highlighted. So anyways, same tool bit, same feed rate, and etc. And the next was a bearing pocket. Now what I've learned with these bearing pockets is that you have tool wear. I mean, I've been using this 3/8 N mill for quite a bit, for a while, and it's potentially, there is some edge wear. So when this surface is set to a bearing tolerance, I wanted a light interference fit, so it's at 1.124 for an 1.125" bearing. When I machined it, it ended up being like 1.122. So I created a separate section, as we note down here, the bottom left, and I did a bearing wear, a totally separate cam portion, so I could come through and edit and fine-tune that pocket. So it's something that I did. I'm having trouble trying to get the end control function to work in the Fusion 360. So every time I go to the machine, it's telling me that there's no tool data or something like that, and I'm afraid to hit go so I don't mess up this part. So I ended up just creating cam and doing it separately. So anyway, we follow up with a chamfer for this. So this wraps up the first cut of the first side, and then we move on to the second side. So the second side is the residual material. So this would be my hole, showing it in a rest machining selection in this setup. So you see there's the two holes in here, and there's hardly any material to zero off of, and plus the potential for inaccuracy. That's why I like to be able to set an origin off of a known machine hole. But in reality, I just rough set it up off this corner and just set a totally separate cam portion for just surfacing it. So it comes through, surfaces it off, and then I have just nothing but the actual part to the dimensions. So I'm able to set my origin off of the part and then complete these cycles here. So we start with an adaptive that cleans out this pocket here, which ends up being just a light recess for thrust bearing to sit in here, and the thrust bearing is for the door of the enclosure to ride up against. So same tool bit, that's the 3/8 N mill, probably 35 thousandths again for the step over at 48 inches a minute, 6,500 RPMs. And then we create another bearing pocket here. Again, this one's set to 1.124. And when I machined it, it came up the same way. It was at 1.22. So again, I created a separate bottom bearing wear cam so I could come in and clean that pocket up. So we go to this pocket. This is for the sensor mount. It was pretty simple, just a little light step in, cut around, and then we do our contour passes. All of these were done with 20 thousandths left over. So we'll come in and do a contour around in here and a contour in the bearing pocket itself. And then here we have a change to a 1/4 inch end mill and do this bore here. This bore is for the sensor shaft, for my proximity sensor, the shaft and the wiring. So it threads onto a mount that sets in this pocket. And then we follow up with a center drill. The center drills all of the future drillings coming through here, and then we drill our number 9 end mill, or excuse me, our number 9 drill bit to drill for the M6 threads that's going in, and then we drill a number 30 for our M4 threads that's going in, and then we finish all that with a chamfer on all of the edges on this surface. And then we tap our M6 first, and we then tap our M4s. Alright, I excluded this M4 because on this particular tapping sequence it's got to go all the way through, and these screw holes are for tightening the adjustment plate that holds the stepper motor, and I wanted a pass through to make sure I had good clearance, that the threads were cut clean all the way through. And this is a blind hole, and I didn't tap that deep. So I have it set here, I believe it was 3/8. Yeah, from the top of the hole down -3/8. So I only needed a little bit of threads to be able to mount this sensor mount. Nothing spectacular. So anyways, that's this portion of it. I'm not really going to cover the cam portion of these other setups simply because they're single hole type scenarios. Like this one, it's a single hole, single thread, so a lot of setups just for single hole when it came to doing these sides. The only side one that was, I believe it was this one. Let me see. Yes. This one has 3 holes and they're M6 threads. And what I did wrong is I machined this side. And it was completely my fault. What I've done, and I completely forgot to read it, when I do my post-processing, I know that you can print out a setup sheet, but I don't feel like printing out all this stuff. So in your post-processor, you can put a program comment and it'll show it up in the top line. So when you go to post-process, you can see your comment, or you can write your comment when you post-process. So now I put a comment on here, stepper pocket left facing. So what that means is that when I machine this, it means this pocket right here should be facing me, and then I zero off this corner to come in and machine these 3 pockets. Well, I neglected to read that and I machined it this way. So I ended up drilling 3 M6 holes here. I did not drill this M4. I figured I could just use the M6 hole that's already there because my enclosure cover covers this up, so you're never going to see it in the first place. So I didn't want to trash a part simply because of 3 holes that were drilled in the wrong and tapped in the wrong spot, but they can still be useful. Anyways, so let's wrap this up and we'll go out into the shop and you can see our progress. So see you in the shop. Hey everybody, welcome to the shop. It's another episode, and this time we're going to machine the drive plate. The drive plate is the section that holds the stepper motor, the pulleys, the bearings, all of that supports the drive or the carousel section of the ATC. This is a pretty complex part, at least for me, as I'm not a professional, but it is a complex part, and it has to have machining on all 6 sides of the actual stock. So this will be a 6 setup sequence. I'm not going to video the whole thing simply because there's just too much to machine, so I'll break it down in segments and show you what we come up with and basically what I'm having to do for reference, etc. But to give you a view, I'll show you the screen of this. So you can see this is the top for the first sequence of machining. It's got to basically do an adaptive, clear all the material around it, and then a boring action which will bore all the way through, which will be used for a later on setting of the origin. And then it's got the pocketing section here for the ATC, or for the stepper motor itself, and then it'll get, that's basically it for this particular setup. So we'll stop it from here, and when we come back we'll have that piece of metal hopefully looking like that. So see you in a few. Alright, we got the top section done, and let me tell you, it wasn't without frustration. I ended up, first time I ever used a 1/2 inch end mill, so I didn't really have a recipe for it yet, so maybe it was a, my mistake in that half. So I ended up breaking my 1/2 inch end mill. So I ended up having to go re-cam it to run my 3/8 end mill. So it ended up taking a lot longer to machine than I expected it to do. So I've had to, and then what I did is I rewrote another cam so I could resize this pocket to have the bearing fit, because there was a slight tolerance offset from that, so it was a little too tight. So I wrote a separate program just so I could sit there and run it until I got the right fit that I wanted on there. So at this point the top half is done. We are ready to rotate it over and go ahead and do the other side. The other side doesn't have deep pockets like that, but it does have a lot of tapping functions in there. So, and another bearing pocket for the other side. So anyways, we'll get this set up and then we'll come back. Okay, so we're machining the bottom half now, or actually all we're doing is surfacing it, so I can get set the origin on the part to machine the bottom half. So sorry you can't really see through the window very well, so I didn't put the camera in there for this short of a process. So anyways, that's what we're doing with this, and when we got it all set back up, we'll touch base again. Alright, the bottom is done, with the exception, as I had to on the top side of it, but on the bottom the bearing pocket's still a little bit tight after I measured it with my telescoping, because I don't have a pin that large. So I need to go into the cam and open this up a little bit. I've yet to figure out how to do it, the in control section in the Fusion 360. Every time I do it, when I come in here, I get a warning or a status basically telling me that the offset or something is not correct, and I'm afraid to hit go and you know, risk ruining a part, especially one like this. So it's easier for me just to go in and create a separate setup and then adjust that setup for boring this particular hole, making it larger. As it's noted before, on the other side I had to adjust by about 1/1000th of an inch to get the clearance on the other side for the bearing to fit in just right. So I'm doing it on this one. So when I get this done, then after that, then it's a whole bunch of setup processes to drill 1, maybe 2, and tap a hole on each of the sides all the way around. So we have to do that next. So let me go ahead and get this sized up, and then we'll come back when we're doing the setup for the other. Alright, voila, we have the mounting bolt. This is the mounting side, mounts this block to the actual bearing rail block pad. So we already have these drilled and tapped. It was pretty close. I had to actually remove it off of my parallels and set it all the way down to the bottom of the vise, because it's just simply, this is my clearance. So that's the only downfall with this type of system, is that you're limited. It limits you on your height of your part basically. But if it misses, it might as well be by a mile. Anyways, this is done here, so we're going to move it to the next setup, and then we'll come back when that's done. Well, we have our first little setup problem, and I made a mistake. I drilled the mounting holes on the wrong side, so I ended up penetrating through the other side. But luckily I can redo this because the actual only bolt that's on this side is a single bolt for the cover. So what I'm going to do is just go through the CAD and change the other two into M4s, and then adjust to fit this particular hole. So no loss there. So really all I need to do is run this program again and put the holes in the right spot. So anyways, we'll get this set up and come back. Alright, we set up the one side, did it. So there's a lot of work to set up just to drill and tap one little hole off in this corner right here. So now we have to take and rotate the part again and drill and tap another hole on the other side. So that is it. We'll come back when it's done. Alright, we are all done. This is the part. All in all, it was a learning experience. This is by far the most complex part that I've made to date, requiring machining on all 6 sides. In the beginning I broke my 1/2 inch end mill. That's simply because I just haven't machined with one yet. That was the first time machining with it, and not learning the feeds and speeds, and you know, getting a proper recipe for it. I probably should have practiced with it a little bit on a scrap piece of aluminum to see what I could get out of it. Instead I just kind of went with the basic setup, and that it turned out to be wrong. First it started out with extreme chatter because of the RPM that I selected, and I could control that a little bit by maxing out my feed rate, but that still in some instances wasn't enough. The second problem was I ignored my setup notes, and I set this thing up wrong,
and drilled and tapped the 3 holes on the wrong side. I mean, I ended up correcting it and putting it on the right side, but as I noted before, a cover goes over the top of this, so in the standard hole was supposed to be an M4, so I can just drill the plate out to be an M6. Not a big loss there, not worth trashing, you know, expensive piece of billet aluminum. You know, the great learning experience was adjusting for tool bit wear, to adjust for the bearings that go in here. I got them with a really you know, a light to medium tolerance or interference fit in there. I didn't want them to be too hard to get in there because they do have thrust bearings this thing sets on. I just need them to be able to stay in place. All in all, it was great learning experience. You know, I'm learning the capabilities of the machine as I go along, and so far I'm really happy and pleased with it. So we're gonna wrap this video up, or this episode up, since this is such a large part and so complex. So anyways, please like and subscribe, and we will see you on the next function of making a part. Thanks.